In March 1944, the Republic Aviation Facility in Evansville, Indiana, completed production on a P-47D-23-RA Thunderbolt. The United States Army Air Forces accepted the fighter on March 18, 1944, as AAF Serial 42-27609. From Evansville, the aircraft moved through Midland, Long Beach, and NAS Alameda before boarding the escort carrier USS Prince William CVE-31 for shipment to the Southwest Pacific Theater. By September of that same year, the operational life of the Thunderbolt abruptly ended. The aircraft was condemned at Dobodura on September 18, 1944, then stripped for usable parts and abandoned in New Guinea. Its exact squadron assignment remains unconfirmed. Current research points to 5th Air Force service, with the 35th, 58th, and 348th fighter groups discussed as possibilities rather than proven assignments. For decades, the heavy fighter sat largely undisturbed in the tropical environment. It was not until the late 1990s that a formal recovery effort removed the surviving wreckage from Papua New Guinea and sent it toward Sydney, Australia. Pacific Rex reports that the aircraft was removed by Robert Greinert and HARS, then placed into storage near Sydney. The objective was to secure the primary airframe for future restoration. However, the surviving public record supports caution rather than certainty about every administrative decision made on the ground. The export history created serious provenance questions, but the public record does not support certainty about the precise legal pressures behind each field decision. Pacific Rex reports that the airframe was de-skinned and that parts were swapped with another P-47 Rec, Serial 42-27608. That second aircraft carried its own confused post-war paper trail, and parts from it are reported as likely having entered later P-47 projects. The safest historical reading is narrow. By the time the material reached Australia, some part and assembly identities had been blurred enough to damage the restoration chain of custody. The reported mixing moved material to Australia, but it also turned provenance into an engineering constraint. In an airworthy restoration, serial identity, production drawings, inspection records, material condition, and traceable part history are safety inputs, not archival decoration. Once those links were blurred, every later load-bearing decision required independent verification rather than trust in the pile itself. The resulting stockpile of aluminum parts presented a massive investigative hurdle. A standard recovery operation carefully tags, maps, and photographs every component as it is removed from the crash site, preserving the spatial relationship of the wreckage. In this case, that spatial relationship was badly compromised. The salvage history effectively turned a coherent technical artifact into a disorganized puzzle. Visual identification alone could no longer prove whether a wing root, a longeron, or a small bracket belonged to Serial 42-27609, or to the second airframe associated with the export history. Years later, when the project changed hands and moved toward an active flight restoration, the consequences of the 1999 salvage operation dictated the entire engineering approach. The mandate was to identify original structural components and reconstruct an airworthy airframe meeting modern flight tolerances. The primary constraint was the complete lack of verifiable provenance for any single piece of metal. Before any physical restoration work could begin, the engineering team had to confront the reality of the mixed inventory. They possessed a massive volume of jungle-recovered aluminum, but they lacked the administrative map required to make load-bearing safety decisions. Historical aluminum that has been subjected to combat loads, impact stress, and decades of environmental exposure requires strict physical evaluation. That evaluation must begin with an accurate understanding of what the component actually is. Origin now had to be established through controlled comparison. That made forensic sorting the first obstacle of the restoration. The geometric footprint of a heavy fighter aircraft presents a massive surface area to the elements. For decades, the surviving wreckage of the Thunderbolt was not sealed away in a protective environment or buried in oxygen-starved mud. By the late 1970s, documented wreck records and photographs show the fuselage center section, wing material, and tail group stored outdoors in a garden near Papandetta. Other stages of the aircraft's post-war exposure are less precisely documented, but the broader reality is clear. The wreckage spent decades in Papua New Guinea conditions before its late 1990s removal. The Papandetta region subjected exposed aviation aluminum to high humidity, heavy seasonal rainfall, and intense thermal cycling. A heavy fighter resting in an open garden is not a static object. It acts as a complex catchment system. The internal bulkheads, lower longerons, and overlapping skin panels can trap standing water. Without active maintenance or drainage, organic material from the surrounding vegetation can accumulate inside unsealed structural voids in the wings and fuselage. The lack of a controlled preservation strategy after the war created exactly the uncertainty that later inspection would have to resolve. The immediate consequence of this open-air storage was not one corrosion mechanism, but an inspection burden. Thousands of fastened aluminum and steel interfaces could hide galvanic action, pitting, crevice corrosion, exfoliation, or possible intergranular attack long after the wartime loss itself was over. The visual result of this exposure was highly deceiving. From a distance, the wings and fuselage center section could retain their recognizable shape. The basic geometry of the heavy fighter could survive long after the engineering margin had become unknowable. Forensic recovery teams must strictly differentiate between surviving shape and surviving strength. An aluminum wing spar resting in damp grass might still look like a solid structural beam to the naked eye. In a purely static museum setting where an aircraft merely rests on its landing gear, this level of unquantified material loss can sometimes be accepted as a display limitation. Returning the Thunderbolt to active flight required a different baseline. The wartime structure had been designed for combat service, not decades of uncontrolled tropical exposure. Any future restoration effort would be forced to assume that the mating surfaces, internal wing spars, and primary rivet lines were fatally weakened until proven otherwise. The long exposure near Papandetta ensured that whatever metal finally left the island would be severely handicapped. The salvage crews who eventually moved the components in 1999 were dealing with shells of aviation aluminum that had been quietly degrading for half a century. By the time the airframe finally reached a professional teardown floor, the visible surface corrosion was merely the outermost layer of a microscopic problem. Restoring a complex heavy fighter requires the precise integration of tens of thousands of individual components. When the project was acquired and transported to the Air Corps Aviation Facility in Bemidji, Minnesota, the engineering team faced an immediate forensic roadblock. Complete disassembly and teardown operations began in January 2015. But the first task was not restoration. It was forensic control of an inventory whose context had already been damaged. The operational constraint forced a strict administrative decision. Air Corps had to rebuild the aircraft's technical map before sorting the metal into restore, reject, or fabricate categories. The engineers instituted a disciplined digital documentation process to regain control of the inventory. Air Corps documentation describes teardown, inspection, part inventory, CAD modeling, scanning, and the fabrication of missing parts from verified drawings and contours. Engineers used historical manufacturing documents, digital models, scans, and fixture checks to map the required hierarchy and part geometry for assemblies, subassemblies, skins, spars, brackets, and fittings. An aircraft structure is not merely a collection of large wings and fuselage sections. It is a dense network of small parts, and each one requires exact identification before it can be restored, replaced, or rejected. This digital framework created a working reference standard for the project, not an infallible historical oracle. Every recovered component could be measured, inspected, and compared against drawings, scans, fastener patterns, and known geometry. That process could identify what a part was, where it belonged structurally, and whether it matched the required configuration. It could not by itself restore a chain of custody broken before the material reached the restoration floor. The digital sorting process reduced guesswork, but it did not make provenance absolute. This evidence discipline prevented unverified material from entering the active flight reconstruction pipeline by assumption alone. It gave the team a controlled sorting method without overstating what the damaged paper trail could prove. The implementation of this tracking method achieved the primary survey objective for the early restoration phase. Air Corps Aviation could catalog, inspect, model, and fabricate the structures needed to rebuild the aircraft. The process re-established a usable engineering baseline even though the earlier recovery had damaged the historical chain of custody. Digital verification could show what a part was and whether it matched the aircraft's required geometry, but it could not prove that aging metal could still bear operational flight loads. The next phase shifted from identity control to material approval. For a flying Thunderbolt, each accepted structure had to survive vibration, engine torque, aerodynamic load, and repeated stress cycles, not merely hold a museum shape. The material review forced the restoration team into a strict physical triage protocol. Critical original components had to be inspected, measured, and evaluated before approval for flight, especially around joints, seams, fastener holes, and mating surfaces where hidden corrosion and fretting could remove the margin that a dynamic aircraft requires. Once corrosion compromises a rivet hole or a mating surface beyond allowable limits, the surrounding component cannot safely be treated as flight structure. The engineering decision was uncompromising. If a structural piece showed unacceptable degradation around fastening points, seams, or load paths, it had to be rejected for flight use. The inspection process required engineers to examine serviceability, measure remaining material, and decide whether a part could be retained, repaired, used only as a pattern, or replaced. As this meticulous procedure moved through the inventory, many original pieces could not be approved for the active airframe. Longerons, ribs, skins, fittings, and other structural members had to meet flight standards, not historical sentiment. The public sources available for this project do not verify a precise 10% original, 20% new old stock, and 70% new fabrication breakdown. The safer statement is that only a limited portion of the recovered historical material could be reused directly, while many rejected components remain valuable as patterns for accurate new manufacture. This boundary represented a harsh collision between historical preservation and active engineering discipline. In the vintage aviation community, there is often an intense desire to maximize the amount of original metal in a restoration to maintain historical authenticity. The team could not let that pressure override airworthiness. The material that failed inspection could not be allowed into the primary load path merely because it was original. Rejected metal still had a controlled use. It could preserve bracket angles, compound fuselage curves, and control cable routing paths that paper drawings did not always capture cleanly. It could teach the shape of the airplane, but it could not carry the load of the airplane. That decision led directly to the replacement strategy. Usable original material where inspection allowed it, serviceable wartime stock where it existed, and new fabrication where safety required it. First, the team searched for viable replacement hardware. New, old stock components could provide an important bridge between authenticity and safety. These were wartime manufactured parts that had been stored rather than worn out in combat, but storage alone did not make them automatically safe. They still required inspection and, where appropriate, non-destructive testing to ensure no hidden defects had developed over decades. Even with surviving stock and recovered material, a massive structural void remained. To complete the heavy fighter, engineers manufactured missing or rejected components in-house to the verified wartime geometry. This finalized the structural safety trade-off. A dimensionally correct new bulkhead or skin panel could be mechanically superior to a fatigued or corroded original when the aircraft was returned to flight. With the primary airframe structure secured, the team confronted a severe mechanical integration challenge. The Thunderbolt was originally designed around a large exhaust-driven turbo supercharger system, routed deep through the lower fuselage. In a modern warbird restoration, retaining that system adds weight, heat, plumbing, inspection burden, and installation complexity. Simplifying or disabling such equipment can be tempting, but in this project the team pursued a much higher level of mechanical fidelity. Air Corps documentation shows work on the GEC-2-3 turbo supercharger, the exhaust system, the wastegate area, the main air intake duct, and the rear fuselage connections associated with the supercharger system, confirming that the fidelity decision reached deep into the lower fuselage. Executing this decision created an immediate thermal hazard control problem. The turbo supercharger system operates by routing hot engine exhaust aft to power the turbine before the gases are expelled. This routing places high-temperature ducting, near structure, controls, and other systems that must remain protected under vibration and flight load. The spatial and heat management constraints forced the engineers to reconstruct shielding, ducting, clearances, and connection geometry with extreme care. A leak or loose tolerance in the exhaust path could expose nearby structure and systems to dangerous heat. To navigate that risk, the team used modern inspection discipline, careful fit, and precise spatial mapping to route intercooler ducting, exhaust components, and related plumbing through tight lower fuselage channels. Alignment, vibration, thermal expansion, and maintenance access had to be resolved at each connection. By refusing to simplify the system beyond recognition, the team preserved rare mechanical fidelity without losing control of the installation burden. The physical machine was finally complete and capable of flight, but it still needed a carefully framed wartime identity to present to the public. A post-restoration test flight marked the administrative threshold from completed reconstruction to validated operation. Because so much of the heavy fighter had been inspected, replaced, repaired, or fabricated anew, the aircraft needed more than visual authenticity before it could return to the modern sky. Modern civil operation demanded a defensible airworthiness basis, verified component tracking, inspection records, maintenance discipline, and operating limitations appropriate to the aircraft. Civil aviation authorities do not grant safety confidence based on historical sentiment alone. The rebuild closed that baseline gap by turning the restored Thunderbolt into an inspected civil aircraft operating under approved limitations. With the hardware structurally complete, the project faced a final historical constraint. The physical machine was technically sound, but its own wartime identity remained incomplete. The original operational combat record of Serial 4-2-27609 has not been positively documented, leaving the restored structure without a verified individual combat narrative. Paint schemes and squadron markings on restored warbirds serve as specific communication tools. When an aircraft lacks its own confirmed combat log, presenting it to the public requires a deliberate interpretive decision. To resolve this missing operational history, the project used a tribute identity rather than inventing a combat history. The restored Serial 4-2-27609 received the exterior paint scheme of Bonnie, associated with Brigadier General William Bill Dunham and the 460th Fighter Squadron, 348th Fighter Group. Public reporting identifies Bonnie as a separate wartime P-47, often associated with Serial 4-2-27884. This practice turns the restored machine into an aggregate memorial. It allows the physical airframe to represent a broader historical unit and pilot story while keeping the surviving serial number separate from the aircraft whose wartime markings it wears. The final operational proof came in mid-May 2023 when the restored fighter returned to flight at Air Corps Aviation. Some public sources report May 15th, while others report May 16th, so the safest phrasing is mid-May unless the production has access to the original flight log. During the first post-restoration flight, the test pilot followed the conservative discipline expected for a heavily restored vintage aircraft. The objective was to verify that the rebuilt structure, sourced components, retained historical material, controls, hydraulics, engine systems, and center of gravity behaved predictably under flight load. The aircraft was reported to have completed the first flight successfully, with contemporary coverage describing the result as effectively squawk-free. That successful return to flight validated the project's controlling discipline without simplifying its history. The final outcome remains a complex engineering success, a heavy fighter resurrected after its forensic chain of custody had been badly damaged. The airframe did not escape the history of the jungle. It overcame that history through reconstruction, disciplined by evidence rather than sentiment. Is a historically aggregated aircraft still the original machine, or an entirely new airframe carrying only the administrative memory of its serial number?